In this lesson, we're going to look at a special limit in calculus. We're going to be looking at the limit of the sine of x divided by x as x approaches 0. Now, in the last lesson, we did look at the limit of the sine of x divided by x as x approaches infinity. So realize this is a different limit. This one is approaching 0. If we tried direct substitution, we would get the indeterminate form. We would get 0 over 0. Now, we're not going to use the squeeze theorem like we did in the last video, because if you tried to take and use that technique, we would say the sine of x is between 1 and negative 1. But then we would divide by x, and when we tried to evaluate the limit of negative 1 over x as x approaches 0, we would see this is undefined. The one-sided limits do not equal each other, and the one-sided limit, one goes off to infinity, the other to negative infinity. So we don't get anywhere using that technique we used in the last slide. So we are going to do this one geometrically. What we're going to do is we're going to look at 3 geometrical figures and see how their areas can be used to show the squeeze theorem for this problem. Now, we see 3 different figures here. We have this large triangle here. We also have the sector of a circle here. And then we have this smaller triangle right here. We're going to use those 3 figures. Here's the angle we're working with, x. We're working with a unit circle, so this point would be right here, 1, 0. Now we know to find the area of a triangle, we know that is area equals 1/2 base times the height. Well, for that large triangle, this here would be our base. So we would have area equals 1/2. Our base would just be 1. Now the height of this triangle is here, and this is our angle. We know this length is 1. We could write our height of our triangle as a trig function. We have the opposite side and we have the adjacent side. We know the tangent of an angle equals opposite over adjacent. So the height of this triangle would just be h equals tangent of x. So there's the area of the large triangle. We're going to do the same thing with the area of the sector and the area of the smaller triangle. We're going to find our formulas that represent the area of those figures also. Now the sector of a circle can, and we're working with the, the sector is here. That's the sector of a circle. Now to find the area of the sector of the circle, we take the entire area of the circle and multiply that by the angle in radians, and we know there are 2 pi radians in the entire circle. The radius of our circle is 1, so we'd have pi times x over 2 pi. The pi's reduce, and we are simply left with x divided by 2 for the area of that sector. So that would give us the area of that sector, and we'll write those formulas in a moment. And last, we're going to find the area of this triangle. So we'd have area equals 1/2 base times height. The base of this triangle is 1 right here. And the height would be here. I drop an altitude from that triangle. And again, we could create a trig function. And this time we're going to use this side of the triangle here, the hypotenuse, and this would be the opposite side. And we know the sine of an angle equals opposite over hypotenuse. And so we know the height would be the sine of x. So we have the area of the smaller triangle equals the sine of x over 2. So the areas that we just found for each one of those geometrical figures. And hopefully you can see where we're heading with this. Do you see that the area of this big triangle is more area than the area of this sector, and the area of that sector has more area than this smaller triangle? So the area of the sector is getting squeezed by the 2 triangles. So we have that feeling of the squeeze theorem. Now remember what our goal is. We're trying to find this limit. So when we build our inequality, we want to end up with the center inequality being sine of x divided by x. So building the inequalities from the areas, we get this inequality. We're going to multiply each term by 2 divided by the sine of x. So if we multiply each term by the 2 divided by sine of x, because if we take the tangent of x divided by 2, I'm working on this one right here, divided by 2, and we divide it by, or let's just say we're multiplying each term by 2 divided by sine of x. The 2's reduce, and we'd have the sine of x. Tangent is the sine of x divided by the cosine of x times 1 over the sine of x. The sines reduce, and we're left with 1 over cosine of x. So we're multiplying each one of these intervals by 2 divided by sine of x. And we end up with this expression and this inequality. Now, when we take the reciprocal, you notice here that we have the we have the x divided by sine of x, but we want the sine of x divided by x. So we're going to take the reciprocal Is this inequality true if I said 5 is greater than 3 is greater than 2? That's a true inequality. But what if I take the reciprocal of each one of these? I get 1/5, 1/3, and 1/2. Notice these inequalities would now have to be switched to keep this true. So when we take the reciprocal, we are going to have to reverse our inequality signs. So now that we've taken the reciprocal, we can take the limit of each one of these intervals as x goes to 0. And we know the limit of the cosine of x as x goes to 0 is 1. We know the limit of 1 as x goes to 0 is 1. Therefore, we can conclude that the limit of the sine of x divided by x as x approaches 0 equals 1. Find the limit of the tangent of x divided by x. We are going to use what we just found to help us solve this problem. Let's just keep this in mind. We know the limit of the sine of x divided by x as x approaches 0 equals 1. We've proved this, so we can always just state this from now on. We are going to, first of all, use direct substitution. We get the tangent of 0 is 0. We get the indeterminate form. So let's try to rewrite this. I could rewrite this as the tangent of x times 1 over x. That's an equivalent expression. And then I'm going to change tangent of x into the sine of x divided by the cosine of x times 1 over x. And then I'm just going to rewrite this a little bit. Could I write this as the sine of x divided by x cosine of x? That's the same expression. And the limit of the sine of x divided by x times 1 over cosine of x is equivalent. And now we can take the limit of each one of these separately. We could say the limit of the sine of x divided by x as x approaches infinity times the limit of 1 over cosine of x as x approaches 0. I may have said infinity, I meant 0 here. We know this equals 1 times, we know the limit of 1 over cosine of x as x goes to 0. We can just use direct substitution. We get 1, and we have found our limit. So our conclusion is the limit of the tangent of x divided by x as x approaches 0 equals 1. Find the limit of the sine of 4x divided by x as x approaches 0. It's important to understand this is called the argument of sine. We can't put anything in there, we can't take anything out. So we can't take that 4 out in front and say, well, we have 4 times the sine of x over x. That's not allowed. We do want this denominator to be exactly like the argument. We want the denominator to be 4x also. And then we can apply our rule. So we could write an equivalent expression by multiplying by 4 divided by 4. Now I have my 4x in the denominator. And this 4 in the numerator I could bring out as a constant in front. So we would have the sine of 4x all over 4x as x approaches 0. Now these are the same, and we can say that limit equals 1. So we'd have 4 times 1, which is 4. So we'd say this equals 4. Now, if you're concerned about this isn't saying 4x goes to 0, if I have the limit of the sine of 4x divided by 4x as x goes to 0, I'm going to make the substitution. I'm going to say let t equal 4x. So we would have the limit of the sine of t over t. Now I'm changing the entire limit into terms of t. So I have to change this in terms of t. Well, let's look at this. As x is going to 0, t is also going to 0. So now we can see, yep, indeed, that equals 1. Another limit. Let's look at this one. This one, let's rewrite it like this. This would be equivalent. So we'd have as x approaches 0. And we could rewrite it as 1/5 times the limit of the sine of x divided by x as x approaches 0. And we would get 1/5 times this limit right here, we know equals 1. So we get 1/5.